All right, this is the first lesson of our chemistry unit, unit number 2. Hopefully you have your note sheet in front of you. Go ahead and get it set up Cornell style. And here is our key question that we will be investigating in this lesson. What are the building blocks of all the stuff in the universe? And before we begin, you don't have to write these down, but it's just something to think about. Get your brain ready. Answer these questions in your head. What is the difference between matter and energy? What is the difference between an atom and an element? Where can you find the different subatomic particles, and what makes an atom unique? If you already know the answers to these, you're in good shape. Otherwise, start thinking about the answers. We will come back to these when we get to the end. So when you touch something, you're touching matter. Matter is anything with mass that has volume. So what do those mean? Mass is usually measured in grams, or if you're using the empirical American version, it's measured in pounds, but it's how heavy something is. So if something if something has a weight to it, it is matter. The examples would be, a bowling ball has mass, and that's easy, but you may not think of this, but air actually has mass as well. The example for that is if you've ever gone scuba diving, the scuba tank is lighter when you come up from scuba diving than it was when you went in. And then volume is measured in liters, or using the American version, gallons, but it's how much space something takes up. And by space, we mean basically if that object or that thing is in a place, nothing else can be there at the same exact time. So if you think of air again, the air around you does take up space. And if you don't believe me, you can blow air out of your mouth and it will your hair on your skin move, and you can actually feel it. And that's because it's taking up space and you're moving it around with your the energy coming from your breath. Now, matter is different than energy. Energy you cannot touch. So for example, you could touch a light bulb. So you turn a light bulb on, you can go up and touch it. But the light that's coming away or flying away from the light bulb, you cannot touch that. So that's the difference between matter and energy. Matter takes up space and has mass. Energy does not do either one of those things. Here's a chart for you. If you already know this, then you don't need to write it down. But if this is kind of a new concept to you, this would be a really good chart to write down. Matter is obviously on the left and energy on the right. So your hand is not energy. Your hand is matter, or is made of matter. But as you move your hand around, it takes energy. Same thing, a drum is matter, but the sound that a drum makes is energy. A lamp is, as I already mentioned, matter, but the light it makes is energy. And then finally, a log. When you burn wood in the fireplace, the wood in the fireplace is matter, but the heat it generates is energy. Now, all matter is composed of atoms. Atoms are the building blocks of everything. They are not actually, though, the smallest particle. Some of you may have been taught that in physics last year or in middle school. They are not the smallest particle. Anything smaller than an atom gets the word subatomic particle. There are 3 of them you need to know about. There are other ones that get into quantum particles. We don't need to know about those. But for us, we need to know the 3 subatomic particles, and they are protons, neutrons, and electrons. And so how are they organized? Well, an atom has 2 parts. It has a nucleus in the middle and an electron cloud around the outside. And again, when you were in middle school, you were probably told the electrons fly in a circle around the atom. Not really exactly true. They do fly around the atom, but they are not in a perfect circle. In fact, it's very difficult to know where they are. You get into some really strange science concepts at that point. Electrons can kind of be anywhere in an electron cloud at any given time. So you could think of it as the electrons flying around the outside in a circle, but it's actually a little bit more complicated than that. The electron cloud is actually much larger than the nucleus. It's approximately 1.0 times 10 to the 5th larger. the actual number for the number that represents that you may have heard of is 100,000 times larger. And that's what 1.0 times 10 to the fifth means. So therefore, that means most of an atom is actually empty. Let me say that again. Most of an atom, in fact, 99% of everything in the entire universe is empty space, because the nucleus is tiny and the electron cloud is, again, 10 to the fifth larger. So this is the analogy I tend to give. That picture is a picture of Qualcomm Stadium. It's the stadium that doesn't really exist anymore. It's being torn down. But if you were to take a penny and you were going to put a penny in the middle of Qualcomm Stadium, the penny represents the nucleus, and the outer ring where the people sit represents the entire atom. So again, the nucleus is incredibly tiny. So imagine right now an entire football stadium completely empty of everything except one penny right in the middle. That's your standard atom. And so I have a video to help you understand that.
Everyone in the world is made up of nothingness. While that may sound grim, it's the truth. In fact, everyone currently on Earth, all 7.6 billion of us, we could all fit into the room you're in right now. The entire human race, every single person, we could all be compressed into a single solid cube with the equivalent size of a sugar cube, all because we're made up of nothingness. What we perceive as solid objects like desks, chairs, cars, even ourselves, they're actually just a big conglomeration of tiny particles separated by what is practically infinite nothingness. This absurd truth has everything to do with atoms. Everything that has mass and occupies a given amount of volume is rudimentarily defined as matter. Everything around us is made up of matter, and even further, everything around us is made up of atoms. Atoms make up everything, but they also exist very, very far apart, and atoms themselves are more void than they are matter. Every atom has a nucleus surrounded by electrons. If the nucleus of the average atom was the size of a peanut, the entire atom would be the size of a baseball field. Around the edges of that stadium exist the electrons, the numbers of which vary by different elements. As a general rule of thumb, nuclei are about 100,000 times smaller than the atoms that they are housed in, making them practically empty space. When you start to consider that atoms are 99% empty space and they make up 100% of the universe, you can start to see you're made up of nothingness. Every human on planet Earth is made up of millions and millions of atoms, which are all 99% empty space. If you were to remove all of the empty space contained in every atom in every person on planet Earth and compress us all together, then the overall volume of our particles would be smaller than a sugar cube. This sounds absurd. It sounds inconceivable, but it becomes much more believable when you consider how much the sugar cube of people would weigh. While the entire human race might be able to be condensed into the volume of a sugar cube, our weight would stay the same here on Earth. This means that the sugar cube would weigh the same as the sum total of every human on Earth. Through some brief estimation, assuming an average weight of 100 pounds, considering that there are kids who weigh less and adults who weigh more, and the fact that there are 7.6 billion of us, we're left with a total weight of 760 billion pounds. That's the equivalent of over 1,000 Empire State Buildings, all condensed into a tiny cube. Try putting that in your cup of coffee. Well, I guess that is if you manage to not be compressed into the tiny human sugar cube. So, you're actually filled with nothingness, and so is everything around you. I guess that means next time you get a bill in the mail, you don't have to pay it, because that's just nothingness too. That's how science works, right?
So there's a model of an atom. Again, this is not really helpful, but you're going to want to write this down, because this gives you at least some idea of where everything is. So inside the nucleus, you have two different particles, the protons and the neutrons, and then you have the electrons in the cloud around the outside. Again, not to scale. If this was to scale, you wouldn't even be able to see the nucleus. So, as I mentioned, there are two atomic particles in the nucleus, really, really crammed close together with incredible density. It's more density than you can even fathom. They're being held together by one of the strongest forces in the universe called the strong nuclear force. But anyway, the protons are in the nucleus, and they are a positive charge, and they have an atomic weight of 1. So for every proton, you increase the atomic weight by 1. Then you have neutrons. With neutrons, don't think of negative, and I know they start with the letter N, but with neutron, I want you to think of a car. If you've ever driven a car or seen your parents or guardian or aunt, uncle, brother, sister drive a car, when they put the car in neutral, the car isn't going anywhere. Neutrons are neutral. They have no charge. So please think of neutral or think of no charge when you think of neutrons, but they also have an atomic weight of 1. The electron cloud has all the electrons, and they carry a negative charge. So the entire electron cloud is highly negative, and they weigh so little that we actually don't factor them into an atom's weight. Do they have a mass? That's a really good question. I've actually read things both ways, whether or not an electron even has mass, which is hard to even fathom, like a particle not having mass, but they're so small, we don't factor them in. Here is a video showing you the difference between subatomic particles and actually how you could actually see them with your naked eye, kind of. So that's how we discovered nuclear reactions. Why is it called nuclear? Because it has to do with the nucleus of an atom. So when you hear nuclear reactor, nuclear power, nuclear bomb, now you know what they're talking about. All right, moving on. So the electrons, they organize into shells, also called energy levels. And then I'm going to often refer, or you're going to hear me talk about them as being rings. The smallest ring or the smallest shell is closest to the nucleus, and it can hold 2 electrons. The next level is larger, and it can hold 8. The third level actually has a really weird shape. And if you got into advanced chemistry, they would teach you about all the different shapes, and we're not going to get into that, but it has a weird shape. It can hold more, but it's stable at 8. So just remember the order that we go is 2, 8, and 8. The electrons are in the outside ring, get a special name, but we're going to talk more about that later. So go ahead and get this down. This is an example of a carbon atom. That shows you the nucleus in the middle, and that shows you the electrons in the shells. Notice how there are 2 electrons in the first shell, there are 4 in the second shell. That's very important. When you're starting to do the work and starting to work out how many electrons are in which shell, the general rule is this, and you're going to probably want to write this down. You always make sure the smallest shells are full first before you start filling the others. So for example, in this atom, carbon has 6 electrons. You don't divide them up 3 and 3. You don't put 5 in the second and 1 in the first. You have to fill the first shell with 2 first, and the leftovers, the other 4, go in the second shell. So again, make sure you have this diagram in your notes. Atoms are organized then by the periodic table or on the periodic table. It's basically just an organized chart of all the elements we've discovered. And you might say, well, what is an element? An element is every atom in the universe with a very specific number of of protons. Those, or that number of protons, is called that element's atomic number. So this is extremely important. This has to be in your notes. Please make sure you remember this. An atom only gets its name because of its number of protons. So for example, oxygen only has 8. It cannot have any other number. If you were to change the number of protons, you change its name. So what makes an atom an atom? One thing and one thing only, its number of protons. You can change neutrons, you can change electrons, you cannot change its number of protons, because if you do, then it's not the same atom anymore. And what is an element? Again, an element is just every atom with the exact same number of protons. All the atoms on the periodic table are balanced, so the number of protons is always equal to the number of electrons. So again, going back to oxygen, if you have 8 protons, you have 8 electrons. And then atoms also have an atomic weight, also known as an atomic mass, which is the number of particles in the nucleus. Remember, electrons don't weigh anything, so we're just talking about the amount of particles in the nucleus. You can actually find or use the atomic mass to find the number of neutrons. The formula is down there. You're going to want to make sure you keep this in your memory banks or write it down for reference later. But to find the number of neutrons, you have to take the atomic mass and subtract the atomic number. Let me explain why. So the mass is all the particles, all of them in the nucleus. The number is just the protons. So basically what you're doing is if you take the atomic mass and you remove the atomic number, subtract, you're removing the protons, what you would have left is the number of neutrons. So we're actually going to practice with that a little bit here in a second. So that's how you read an element box. The atomic number is always on the top. So when you're looking at an element, when your eyes go to the top, you're always going to the atomic number, and that's the number of protons. The symbol is the letter or letters. In this case, it's N, but you can also have two letters like Ca is calcium, and there's others. Na is sodium, sorry, skip my mind for a second. But the symbol is the letter, the capital letter. By the way you write element is capital letter followed by a small letter if there's two. The element name is usually underneath the symbol, and then the weight is always on the bottom. Now, how do you use this? I have a video to help you remember.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about reading the periodic table. Periodic table gives you lots of information about the different elements. Let's get started with carbon. If you'll notice carbon, it has an atomic symbol of C, which is the capital C. Let's first focus on how to find the number of protons, neutrons, and electrons. The number above the atomic symbol is the atomic number. In this case, it's a 6, so it tells you that it has 6 protons. Protons have a positive charge and gives the elements its properties. It can never vary. Next, let's figure out the number of electrons. Unless the element is an ion, which means it has a positive or negative charge, it will have the same number of protons and electrons. So since you have 6 protons, you will have 6 negative electrons. Next are the number of neutrons. You will see under the C is a number 12.0096. That is the atomic weight. It's the weighted average of the number of isotopes. But you need the mass number for the number of neutrons, so you will round it to its nearest whole number, in this case 12. Then you can use the formula mass number equals protons plus neutrons. So you have a mass number of 12, you have 6 protons, so you need 6 neutrons. Now a couple of extras. Notice the color of the background. There is usually on a periodic table a key that tells you what the different colors stand for. In this case, the green is a polyatomic nonmetal. And also, the atomic number can be different colors. In this case, it is black, and the key tells me that this is a solid. And finally, you can look and see what column it's in, and it will tell you its family. Elements in the same family have similar properties and the same number of electrons in the valence levels, except for the elements in the middle. Okay, let's look at another example. Let's look at boron. Boron has a symbol B. It has an atomic number of 5, so it has 5 protons, so it will have 5 electrons because it's neutral in charge. It has a mass, it has an atomic weight of 10.806, so I will round that to 11. Then 11 equals 5 plus 6, so it has 6 neutrons. It is a metalloid based on its color. It is a solid, and it is in family 13, so I know that it has 3 electrons in its outer shell. So there we go, some hints on how to read the periodic table. Hope this helps, and thanks for watching.
And that's how you do it. That's another way to state the exact same formula that I already mentioned. All right, so let's test yourself. Ready? Take a look at that element. It's obviously oxygen. I've already mentioned it. The symbol is O. That's not a 0, that's an O. But take a look at its atomic number. Take a look at its atomic mass. Ready? Ask yourself, how many protons are in this element? How many neutrons are in this element? How many electrons are in this element? Pause the video, answer the questions as best you can, and when you're ready, when you've done that, Restart the video to see if you're right. And here are the answers. So oxygen has 8 protons. Why? Its atomic number is 8. Remember, 8, the number on top, is always its atomic number. The neutrons, you take that 15.9, you round it up, and you get 16. You get 16, which is the mass, minus 8, the number of protons, and you get 8, and that's the number of neutrons. And remember, the number of electrons on the periodic table is always balanced. So it's 8 protons, and then so there must be 8 electrons. That number will change as we do more chemistry work, but just for now, keep that in mind. Let's test ourselves one more time. This element is called sodium. Go ahead and test yourself. See, can you figure out the number of protons, the number of neutrons, and the number of electrons? Pause the video, see if you can figure it out. And when you're ready to check your answers, restart the video. And here are the answers. So there's 11 protons because the number on top is 11, that's its atomic number. The number of neutrons is 23, the mass, minus 11, the number of protons. So what's left? The number of neutrons. And remember, everything on the periodic table is balanced, so the number of electrons is 11. So let's go back to our key questions that we started this lesson with. Do you now know what is the difference between matter and energy? Do you now know what is the difference between an atom and an element? Can you find the different subatomic particles? And when I say find them, I mean where they are in an atom. And then finally, what makes an atom unique? Or another way to say it, what thing gives the atom its name? What is only true about one atom or one element in the universe? Think about those answers. If you can answer those questions right now, you are in good shape. If you cannot answer these questions right now, you do need to review your notes because those look like very good test questions. So right now, what you're going to do, you're going to go over to the left side of your notes, do your filtered notes, which is condense all the notes you just wrote down into some key points that you know you need to remember. And then I want you to set your notes to the side, go do something else, even for a little bit. It could be as little as 15, 20 minutes, half an hour. And then I want you to come back and I want you to try and write a summary without looking at your notes. See if you can. If you can, great. If you cannot, go back to your notes and use them to write a summary. A summary is a 2 to 3 sentence review of everything you just learned. And once you're done with that, you're done with this lesson, and I appreciate your attention for today's lesson.